Hello everyone, my name is Brian Arenas. I am a electrical engineering student at Universidad Pontificia Bolivariana in Bucaramanga, Colombia. And I'm here to present our project development of an algorithm that predicts hand movement in the game rock, paper, and scissors with the use of time, MR, and Arduino Nano BRE33. This project is the result of the application of an incredible team. I would like to take a moment to introduce the members of them. Emmanuel Radita, he is our electronic engineering student. Daniel Russo, he is our electronic engineering student. And Silvia Sotelo, she is our research group leader. Each of them has played a crucial role in the development of this project, contributing their unique skills and commitment. Before I continue, I would like to express my deepest gratitude for the opportunity to be here today, and it's an honor for me to represent our team and share with you the fruit of our labor. Rock, paper, scissors is a simple but fascinating game that has been popular for centuries in cultures around the world. It is played with the hands and is based on three gestures. Rock, which is represented with a closed fist, paper, which is represented with the open hand, and scissors, which are represented with two standard fingers. The game follows a cyclic mastery role. The rock crushed the scissor cut the paper, and the paper was around the rock. In each round, players reveal they choose at the same time. Whoever chooses the dominant hedge wins the round. It's a game of chance, strategy, and psychology, and despite its simplicity, or perhaps because of it remains a favorite around the world. Our project aims to develop algorithms capable of identifying the three different movements in the game. To achieve this goal, we have used the Arduino Tiny Machine Learning Kit. This kit has provided us with the necessary tools to capture, process, and analyze the data necessary for our algorithms. The Tiny Machine Learning Kit is a powerful tool that allows us to develop an experiment with machine learning application in a compact and accessible format. This kit is especially relevant to our research for several reasons. The Arduino included in the kit comes with a variety of built-in sensors. This sensor allows us to capture and analyze hand movements in real time, which is essential for identifying where people see such gestures. Also, the kit allows us to implement machine learning algorithms directly on the device. This means we can train our model to recognize rock, paper, scissors, headshot directly, and result in a fast and efficient response. Uh, with each passion board and program keyboard, the kit makes it easy to connect with additional components, such as OV17675 camera and program device. Uh, Also provide us with the necessary tools and capabilities to carry out our research in an efficient and effective way. In this slide, I'm going to show you the Reno Nano BRE. The Reno is a compact and powerful board either for machine learning project and application. This board is important for the project since due to the variety of built-in sensors it has. It makes it extremely versatile for a wide range of applications. Sensors built into the Reno Nanos include temperature and humidity sensor, barometer, ambient light sensor, accelerometer, and gyroscope. These sensors can measure linear acceleration and velocity respectively. They are essential for applications such as motion detection or orientation. Microphone. In the project, we analyze the data from the accelerometer and the gyroscope. Since, as I said previously, these are used in application for motion detection or rotation. Now, I'm going to explain the experiment. The project collected signal from individuals of various age and gender, which with the majority being university student participants were played in numerical order, 1 with 2, 3 with 4, and so on. Each was provided with a glove equipped with Arduino BRE. They were instructed to play 4 rounds of rock, paper, scissors to synchronize the start and end of the rounds between the pairs. And a recording was used, indicating when to start and when to stop. Each participant was assigned an individual computer to collect data through the Edge Impulse platform. 2 members of the research team recorded movements of each participant. The capture signal were uploaded directly to Edge Impulse, which stored the data set. We had diverse group of participants. There were 28 men, 20 women, and 1 non-binary. Starting with the scissor strategy, there were a total of 79 games played. Interesting, almost half these games, presenting 48% at a time. Moving on the paper strategy, it was used in 76 games. The tie rate was slightly lower than the scissor strategy, standing at around 39%. The win rate was almost similar at 28%, but the loss rate was a bit higher. The rest strategy was used in 69 games. The tie rate was 42%, which is slightly higher than the paper strategy, but lower than the scissor strategy. The win rate for the rock strategy was 24%, which is lower than both the scissors and paper strategies. In the golf paper, rock and scissor hand movements are crucial. Each option, rock, paper, scissors, has a specific hand shape and different movement. This is where the accelerometer and gyroscope come into play. The accelerometer measures the linear oscillation of the hand. This can help identify the speed or direction of hand movement, which can be used for predicting game movement. On the other hand, the gyroscope measures angular velocity, which helps understand the rotation of the hand. Different moves in the game can have different rotation patterns. Therefore, by analyzing the data from the accelerometer and gyroscope, we can obtain a detailed understanding of the hand movement. This can be used for predicting the game move in the game of paper, rock, scissors. Emmanuel?
Hi everybody, I'm Emanuel Angarita, a student of electronic engineering at Universidad Pontificia Bolivariana, and I'm going to talk about our workflow and the current state of the algorithm. First of all, where is TinyML? We have been using this term a lot. Well, TinyML is the application of machine learning in microcontrollers, small devices with limited resources. As my friend shared with you, the Arduino Nano 30T BLE has only a single core, which compared to the cores on our computers, it is very slow. It is very dumb and low capable in all aspects. It has a very tiny amount of memory. To give an example, these slides will take around 30 times the RAM capacity or 7.5 times the flash capacity of the Arduino. But the microcontroller has many advantages that the computer don't have: portability, energy consumption, size, and peripherals. The microcontroller is very small and it doesn't consume much energy, allowing us to use it to make portable devices, wearables, off-grid devices, in-situ computing, and control peripherals like PWM generators, ADC, DACs, and GPIOs allow us to interact with the real world, like turning on and off lights, controlling motors, doors, machinery, and all of that with a single chip or SoC, system on chip. Because the microcontroller don't have a lot of computing power, the workflow of TinyML requires work on different devices. First, we will have to collect data for our model. In this case, we collect data from the same hardware that we will use to deploy the final model. But if you import external data, you'll have to make sure that the data is represented on the same way on the import dataset and on the final hardware. This step we accomplished it with the experiment. Now, we'll put the microcontroller on the side and move to the computer, because we will need that extra computing power. Next, we'll process the data, analyze it, clean it, and if we want to make some transformations, we'll make it. After that, we'll split the data into sets, one for training and the other to test the model with data that it hasn't seen previously. After that, we will create and train the machine learning model using TensorFlow. Up to now, the developing process is very similar to developing a user machine learning model that will be executed in our computers. But here comes the twist. Because the microcontroller will run the model and it has very limited resources, we need to transform that model into a series of simple instructions that the microcontroller processor can execute with its available tools. This is done with TensorFlow Lite. After the model is trained and validated, we will export it to a C header file with binary data describing the trained model. Next, we'll import the header file to the source code of the final algorithm. This source code contains all the logic that the microcontroller will do. Besides the machine learning model, we have peripheral initialization, data capture, data preprocessing, memory management, result reporting, user interface, between others. Next, we will build and upload the code to the microcontroller, and our work in the computer has finished. Finally, we can test our algorithm in the microcontroller, and if we have to make some adjustments or modifications, we'll have to repeat the previous steps. In a summary, we capture the data with the microcontroller, train it in a powerful computer, and deploy it on the microcontroller. In this slide, we have our current model architecture. We are using a dense neural network with two hidden layers. The first one has 50 neurons, and the second one has 15 neurons. Both layers use ReLU as its activation function, and output layer with 3 neurons, each one representing each movement: paper, rock, and scissors. This final layer uses softmax as its activation function. This is a work in progress, and we are still looking for the best architecture. This is a collective work of the research hotbed Bcemic, and I want to thank all the team for the work and compromise with this project. Also, I want to thank Edge Impulse and the program Edge Impulse University, which donated 10 Arduino Tiny Machine Learning kits. This hardware provides us the opportunity to explore the world of TinyML and machine learning. We are very excited about this area of research, and we have other projects in parallel that we have the hope to share it in the future. Finally, thanks to the ICTP for allowing us to participate in this workshop and to share our experience, and thank you all for your attention.